Hello, everyone. Welcome to the session of the problem-solving course that has to do with grammars. So grammars are a fundamental tool in computer science, and you will meet them in several guises in the rest of your studies and also in the future of your careers in computer science, no matter what you will be doing. So it's a fact of life that in computer science, we use languages to communicate with machines. We use programming languages to write programs that instruct machines to carry out some computational tasks that we want them to carry out. And in fact, increasingly more so, because now computing devices are just about anywhere embedded in every facet of our society. We also use languages to describe what kind of tasks programs are supposed to carry out. And these languages are called specification languages. Now, all these languages, like the natural languages that we use in everyday life to communicate amongst us humans, have a syntax and a semantics. Now, the syntax of a language is going to describe exactly what kind of correct phrases, expressions, sentences we can come up with in the languages that we use. And whereas for natural languages like Icelandic, defining precisely such correctness criteria for phrases and sentences is very difficult and perhaps not that useful at all unless we want to do machine processing of natural language. For computer languages, that's absolutely vital. Just like for natural languages, we describe the syntax of the computer languages that we use to communicate with machines by means of grammars. Now, a crucial difference between the use of grammars for natural languages and for computer languages is that the grammars that we use to communicate with machines, to describe the languages that we use to communicate with machines, have to be fully formal and precise. And there is a good reason for that. And that's because sort of machines do not understand imprecise, possibly ambiguous definition. Machines are the most precise creations of the human mind. And to interact with them, we have to use a standardized language, which is so standardized that everything in it has to be fully and formally specified. This may sound like a straitjacket, and perhaps it is, but it has a lot of benefits. A crucial benefit is that once we have defined the syntax of our favorite language by means of a grammar, then people have devised algorithms that generate from this grammatical description of a language, algorithms that we can use, for instance, to do syntax checking. And this happens all the time inside the compilers that you interact with on a daily basis whenever you write a program and you want your machine to execute them. Let me give you a couple of examples by way of motivation. As I've already told you, in programming languages, we use grammars to describe exactly what are the legal programs that any compiler for that language should accept and that any machine should be able to execute once the program, the source program that you feed to the compiler, has been compiled into assembly or machine code. In this way, grammars really generate describe the programs that are correct and can be used to generate at the press of the button programs, which are called parsers, that actually do the syntax checking for you. And parsers are really a crucial part of the front end of your compiler because not only they check for correctness, not only they tell you that you missed a semicolon at line 59 of your program or that you made some other perhaps silly syntax error, but they also do something which is fundamental for computer science as a whole and for programming and for you whenever you generate and run your programs. Given a syntactically correct program, a parser would generate a so-called parse tree representing exactly the syntactic structure of your program. Now, this parse tree is a kind of data structure that is going to take the form of a tree that really describes why your program is syntactically correct. And once this data structure is being constructed, then it can be used to perform any kind of analysis of your program. For instance, find types for the program fragments, for instance, generating the target code that will eventually be executed whenever you actually run your program, and do lots of other interesting things. Another typical example, which is very common today in the age of the internet, of the use of grammars, is in describing important components of XML documents. Now, XML is by now a de facto standard for describing documents that are going to be put on the internet. And an important component of an XML document is the so-called document type definition. Now, what is a document type definition? It's really nothing but a grammar. It's a way of defining formally what are the legal building blocks that can make up an XML document of a given form, together with some description of what are the legal elements and attributes of components of this document. And any legal syntactically correct document has to conform to the grammar description given by the document type definition. So now motivation is over, if you wish, or some of it. It's time to ask ourselves exactly what a grammar is in computer science and how we can actually use it to generate a language. So let's do that by means of a simple example. So let's assume, for instance, that we want to describe a little grammar that is going to generate some simple arithmetic expressions. So in these arithmetic expressions, we can use variables, and expressions can therefore be variables. Now, what I'm writing right now is what is called a rule or reproduction of the grammar. On the left-hand side, you're going to see something which we call a non-terminal of the grammar. Non-terminals are going to describe syntactic categories of your language. So this could be in a programming language expressions, statements, Boolean expressions, arithmetic expressions, whatever is of interest. Var is also a non-terminal. The arrow says that whenever you have in a string that you're trying to construct an occurrence of the name AXP, you can replace that name by var. Now, an arithmetic expression could also not only be a variable, but it could also be, say, the sum of two arithmetic expressions. Here, the symbol plus, which I'm going to underline in red here, is a so-called terminal. A terminal is going to be one of the characters that will eventually compose a string that we can generate from the start symbol, the start non-terminal arithmetic expression AXP. Now, eventually, we also have to say what is it the variables could be. So let's assume that we have two names for variables. The variable could either be X, or a variable could be Y. Of course, there could be more, but sort of this is just to keep the example grammar description simple. Now, both X and Y are going to be also terminals. That's why I'm going to underline them in red. So This grammar consists of two non-terminals, which are AXP and var, and three terminals, which are the plus symbol, the X symbol, and the Y symbol. And four rules or productions. Let's number them from top to bottom. Now, what is the role of these productions? Well, the goal of the game is to use the production starting from the start non-terminal, which for us is AXP, to generate strings that consist only of terminals. So let's assume, for instance, that we want to generate our goal is to generate the string, which is X plus Y, using the rules that we have at our disposal. How will we do that? Well, first of all, we need to choose one of the two productions for AXP to rewrite the symbol AXP into something that looks like our goal. So I think the only safe bet, you would agree with me, is that we use the rule number 2. And let me label this rewriting step with number 2 to say that we've used rule number 2 to rewrite AXP into the sum of AXP and another AXP. In so doing, we will have achieved the plus symbol in the middle. We have generated the non-terminal, the terminal plus in the middle. So what we want to do now is to replace the first AXP with X. How are we going to do that? Well, the only thing that can rewrite to an X is the non-terminal var. So what we want to do is to get the var instead of the AXP, and we can do that by applying the first production, because the first production tells us exactly that we can rewrite, whenever we have an AXP, we can rewrite it into a var. Now we are in business because we can use the production number 3 to rewrite the var into an X. So we have X plus AXP. And now we are nearly done because we have also obtained the X at the front. We have obtained the plus that follows it. And now all we need to do is to rewrite the AXP into a Y. Well, not surprisingly, we can do it in exactly the same way as we did to obtain the X instead of the AXP. The only change is that after having rewritten the AXP into a var, by using again production 1, we can now rewrite using production 4 the var into a Y. And lo and behold, we have obtained the string that we wanted to obtain as our goal. Now the rewriting can stop because we have achieved the string that only consists of terminals. And we are done. The language that can be generated by a grammar, like the one that we've just considered a simple example, consists of all of the strings of terminals that you can obtain by applying the rules, the productions in the grammar, starting from the start symbol in all possible ways. And the language describes essentially all the syntactically correct arithmetic expressions that can be generated from this simple grammar. Now, all that you're left to do is to get stuck in, read the document that accompanies this course session, which contains a collection of exercises apart from a description of a grammar that essentially repeats in more detail what I've just told you, it also consists of a collection of problems that you can try to solve of increasing level of difficulty. These problems will allow you to experiment with your understanding of grammars and, I believe, have fun. So have fun and get stuck in.